And it is, yeah, apologies. I misread the question the first time. I, for some reason, thought you were talking about space-based telescopes. Mitigation strategies are big at the big observatories right now, trying to figure out ways around having satellites photobomb every image that they take. Right now, I think the most effective method is predicting when a satellite is going to be passing through your frame and just closing your shutter for that second it takes for the satellites to pass by. But as time goes on, that method is going to become less effective as there are just more and more satellites. So we also need to be taking into account mitigation strategies like how do you build satellites that don't reflect as much light, that don't show up in my images? And maybe do we need that many satellites that are constantly in the air, in the sky? So that's a big topic, especially for astronomy, because astronomers have kind of been saying this for like a decade that, hey, this is going to be an issue. And a small subset at least. And now a lot of other astronomers are like, oh yeah, this is actually kind of a bummer. Oh, that's really cool. Space sustainability is your topic. Yeah, it's a really, not something I had actually dipped my toes into until maybe about a year ago when I started working on a satellites project. But it's very, very interesting.
Just to go back to I don't know if we close the loop on the amino acids question. So to my understanding, amino acids, you need something like a mass spectrometer to actually, or like electrophoresis to actually see those signatures from amino acids, which means you have to be in situ. You have to be there to collect a sample and actually put it in a instrument and analyze it. When we talk about finding life, so that would work in the solar system maybe, where you could send a robotic probe or something. In exoplanets, we're basically looking at spectral signatures. Oh, it looks like YouTube is back online. Awesome.
Yay.
Thank you, Paul. You're basically looking at spectral signatures in the atmospheres of these planets. So you were looking for atoms or molecules that emit or absorb light at specific wavelengths. Amino acids are proteins. They're big. They're large compared to atoms and molecules. And so I don't think they have those types of signatures, at least not with the strength that you would need to detect with our current technology. So yeah, so I think the answer is outside of the solar system, I think amino acids are currently off the table. Inside the solar system, I think we may have seen, if not amino acids, the ingredients for them, the building blocks of those proteins. I think we may have found them on in like the material of comets that we have flown sample return missions through. I want to say that's the case, but could be making that up at 5 in the morning. We're actually rapidly approaching sunrise. So I'm going to spin the wheel one more time.
Yeah. I'm actually going to go out because I think we are hitting the point where we don't have time for another large observation on the eVscope. So I'm going to go take some darks and then park it.
Great.
Rajaf, you asked about reaching out. I would be happy if you wanted to send me an email. So I am on the SETI website under Ryan Lambert. You can just send it to rlambert@seti.org as well. But yeah, just find me on SETI and feel free to drop me an email. Just let me know who you are so that I don't mistake it for, I don't know. I get a lot of random emails from people I don't know. So just let me know who you are in the beginning and I'll be certain to check it out. So yeah, right now our eVscope that has been doing asteroid observations has basically hit the limit. So I'm going to finish this off by putting the cap on it and take some dark frames and we'll put it to bed.
Well, I spun the wheel twice by accident. We got the same one. So we're going to look at the Dusty Hand Galaxy whether we want to or not. This one is a challenge, chat. I don't know If we're going to see anything with this galaxy, I've never looked at it before, but I saw that it might be a possibility. So I got to look up the NGC number, 2146. 2146, the Dusty Hand Galaxy. Let's give it a shot. This might be our last target of the night. We'll see how it goes. If I look at our agenda, or maybe my internal agenda here, 12-degree dawn. So the beginning of, or the end of nautical twilight. Or sorry, the end of astronomical twilight. It's 5:40 a.m. 5:45 a.m. local time. So that's 45 minutes from now. That's about the time we generally stop observing. And probably when we'll do that, we will shut down the eVscopes, pack them up, and probably close up the nickel. We might go in and go into the dome and watch the dome slit close, because we didn't get to see it open at the beginning of the night. We can watch the telescope park itself as well. And then we'll probably take some calibration frames, dome flats. I don't know if we'll take dome flats. We'll see. We'll see how much energy Ryan and I have. We might take some dome flat calibrations. We will probably take bias frame calibrations. Those are simple, but we'll describe what those are. And then around 6:15, yeah, 6:30 we'll probably sign off. 6:36 is sunrise, so we're almost there. Let me hide the wheel of targets again. All right, we are on target on the Dusty Hand Galaxy. We'll see what's here. This is a new one for me. The nickel has finished exposing. We will take 5 more images. We've gotten really good data tonight on this asteroid. So I think we've gotten, again, we started around 9:45 maybe. No, it took us a little time to get on target with the asteroid. So maybe 10:30 p.m. We're going to go to about at least 5:30 probably a.m. 7 straight hours of data on this asteroid. That should let us build up a pretty good light curve. We'll get to work processing that probably on Monday. I'll be honest. I had hopes that I'd be able to have something that would show us the light curve in real time, and ran out of time. It took a little longer to get the logistics sorted out for making tonight work, and just did not get to finishing it. But my pipeline to process the data is mostly done. So probably work on that on Monday, Tuesday. And we'll post the results somewhere, probably on the Unistellar Citizen Science webpage. We'll certainly share it in the Unistellar Citizen Science Slack. So if you are an eVscope user and you haven't joined that yet, please open up the Unistellar app, go to the Science Mode tab, and then click the Join Mission or something like that button at the top. Fill out the form, and you'll get an invitation within a week or so to join our Slack channel. Then you'll be on the inside. Oh, we got a tiny little galaxy. Tiny little galaxy. Full of tiny little aliens. Yeah, we'll see if that gets any better. I should probably Google why it's the Dusty Hand Galaxy. Let's see. Yeah, nothing immediately obvious comes up. So if anyone knows, drop it in chat. Let's see. We've got some new folks joining. Thank you for tuning in. We're winding down here, but we've still got some things to talk about. What do you think of life thriving from a robotics business to Europa? Yeah, I mean, we might have discussed this before you joined. There is a branch of kind of solar system exploration called planetary protection that not only protects the Earth from external microbes and things, life forms, but also protects other worlds from our microbes. And so they do their best to clean our spacecraft anywhere, because that is a concern. We don't want to, if we can help it, we don't want to go seeding other planets with our life. If there is life there, we don't want to obliterate it with our own. Let me see, is this image weirdly bright? It is. Keep an eye on these nickel. Let me see, I'm going to poke my head out the window and see if the sky is getting brighter yet. Not particularly, but we may be, we're getting pretty low on the sky. We're at air mass 1.7, which is indeed pretty low on the horizon, towards the horizon. We could be getting either light pollution from San Jose. Maybe there's a little bit of marine layer fog down there close as well. Or we just got some stray light in the telescope for an image. Keep an eye on it. But yeah, that's kind of my thoughts on there. I think we should probably try to keep our critters off of other planets if we can help it. Off license, thanks for tuning in. Have you ever imaged any galaxies without a dark matter halo? I know they exist. I don't really image galaxies, so the answer for me is no. I don't know if Ryan has. I know actually Ryan has mostly worked on the opposite. He worked on a lot of dwarf galaxies, which are much more dark matter than most galaxies compared to the normal matter that's there. But yeah, I think I have heard of these galaxies that have less dark matter than expected, but that's all I know. Let's see. You're welcome, Rajas, for the stream. Left side looks kind of like fingers in the galaxy. Yeah. Yeah, I sort of see it. Let me see if I can touch this up a little bit. Kind of tune up the brightness. Yeah, it's tiny. It's a tiny little galaxy. We might give it we'll give it a few more minutes and then maybe move on. Yeah, anything that you missed from earlier in the night, this stream should be recorded and available on YouTube at the very least. Ryan's got a telescope. This is an eVscope. We didn't really show it off before.
I did not think this through either. I should have brought that
up. The backpack.
Yeah.
Yeah, sorry, I didn't really mention that.
Yeah, you didn't, did you?
No, that's an eVscope. Tiny little one, but it's powerful. Careful now.
I'm trying already. I got an iPad strapped in my hand.
So yeah, you can see there's the entrance aperture up top. The camera is mounted right here in the middle of the entrance aperture on a secondary support, and then the primary mirror is at the bottom. Where's the lens gap? Probably here. There's one here. There's one in the back, and it sits on a tripod. Camera, computer, motors all built in. Yeah, Ryan, I think our nickel data may be getting a little worse damaged. I think, yeah, either the sky is brightening
There are clouds.
Or it's cloudy. Okay.
Yeah.
Down.
I sent you a text, but I was connected to an eVscope.
Oh, sorry, I didn't get it.
No, yeah.
Okay, that makes sense. We'll keep taking data. Never hurts to have data.
That was why I couldn't see stars on this one, so I assumed I was like, oh, okay, it must be getting kind of bright. And then I thought more about it as I was walking down. I was like, that doesn't really make sense considering you see stars on yours.
Yeah. Daffodil Simmons, thanks for joining. What do you get from the asteroid light curve? Carbony versus irony. Mostly we get, we're trying to get the rotation period. So the light curve shows us how the brightness of the asteroid is varying over time. So we're seeing different surfaces of the asteroid reflecting sunlight, and seeing how that pattern of brightness repeats over time will tell us how the asteroid, how quickly it's rotating.
Daffodil Simmons, what do you think about cool stars?
Do you know this person, perhaps?
Yeah.
Okay. But yeah, I don't know that we get much out of the composition. Maybe from the color that we. No, not really.
Not particularly.
Okay. Not from the light curve itself, for sure. I would say, but
I think you can. I think you make some correlations, but it's hard.
Okay. That's not our goal, at least. Our goal is to get the rotation period, and we might. We might be able to tell multiplicity if it has a moon or not.
Yep.
That's a next level goal.
Yep. Largely, it's you can just get the shape as well after all that.
Yeah, and the three-dimensional shape. Can the software model and remove stray light sources?
I should have asked his opinion on phosphorus.
Can the software model and remove stray light sources? We're talking about the eVscope software. The eVscope will, indeed, it does filter out background light, which is mostly light pollution. It will remove, for example, moonlight if you have moonlight leaking into your images. There, of course, are limits to how much you can do with any sort of software. At some point, if your images are just really bright from a stray light source, like a street light or something, you just lose sensitivity, and that's that. But yeah, the eVscope does that internally in real time in its software. The nickel doesn't do anything but take images. We will do all the processing ourselves afterwards, and implement the same type of spatial filtering, for example, that the eVscope does to remove light we don't want. Tried to study a few traditional calendar systems. Oh, I see. And the calculated twilight times aren't helpful. Any thoughts? Sure, I understand the traditional calendar systems. Do you understand?
What?
Steve Bos's question.
Tried to study a few traditional calendar systems. Twilight times aren't helpful. I need to know what the context for that is. Aren't helpful to what?
Yeah.
Because that depends on what you're trying to do. Give us a little more context. We can maybe answer some more, or hopefully give you a better answer.
Spinning the wheel one more
cool
time.
Cool stars are brown dwarfs. That was a losing my words at 12 hours and 17 minutes. That was mostly just because I know who Daffodil Simmons is. He's a fellow astronomer. Just being a dork. So are light curves how we know that interstellar object 17 is oblong? Like stars, they're easier to see than asteroids. I don't remember how we got the shape of Oumuamua. I would believe that, it would make sense that it was light curves.
I think they hit it with a. Did they hit it with a radar too?
Oh yeah, that's true.
I'm not sure if they did.
I forget radar exists sometimes.
I believe Oumuamua was already past Earth and on its way out the solar system before we saw it.
Yeah, we tracked it backwards, and that's when we're like, oh wow, that's moving way too fast to have been in the solar system.
Yeah, so I actually don't recall. But they may have pinged it with radar.
Yeah.
And
so radar gets around the issue of trying to shape things with light curves by just giving you the shape. Using light curves, you kind of have to estimate. Based on how the light curve changes, as the phase changes, so as the position between the sun, the asteroid, and you
changes, you can start to piece together what the shape is. But if you just get radar, you just like basically see it.
Yeah.
But it's shorter range.
Yeah. So let's see. We're gonna give up on the Dusty Hand Galaxy. So burn that image into your brain.
God dang it.
Remember what it looks like for a whole time, and then we're gonna move on. It was worth. I like seeing the Dusty Hand Galaxy. I might come back another time. Certainly not on my Mount Rushmore of galaxies. Let's see. It's a very American joke, I just realized.
Yeah.
Not in my top 4. Let's see. We're going to try Bode's Galaxy. We'll go to that. That's in the east. I'll look up where Jupiter is, Bruno. Might be setting. Jupiter. 67 degrees south-southwest. That's tricky. Could be behind the dome. It might be obstructed by the nickel dome. If Bode's Galaxy fails, we could try Jupiter, but try Bode first. So either the telescope is okay. I think it is getting cloudy.
Yeah, we are hitting. It's like where they're still kind of thin and patchy, but it's getting cloudier.
Okay.
Oof. There was a point where it was looking like it was going to be clear when I was packing up the telescope, but I must have rolled
We
back
still
in.
see stars. We can see the galaxy here.
Yeah.
Let me just touch up the centering a little bit here. All of our go-tos have been absolutely perfect. You can see the clouds moving through, probably either fog or clouds. You can see them moving through the image as we watch. It's that splotchy brightness.
Mm-hmm.
So let's see. Just to keep our, I'm going to start the enhanced vision on the eVscope. Quick look at the dew sensor, humidity sensor. All right, the telescope humidity is fine. So they're probably high-level clouds.
Yeah.
That's okay. Just want to make sure the nickel is totally safe. So we could switch to like R or I band if we want, but kind of inclined to just ride it out in V.
Yeah, I say we just see what happens.
Um,
Oh yeah, good to see you. Looking forward to talking with you.
Thanks for tuning in. What filters do you have for imaging the galaxy? We have B, V, R, and I.
No, that's
sorry,
that is for the asteroid.
For the eVscope.
It's a Bayer matrix, so it's it has the red, green, blue.
Yeah, I mean the telescope is really it's unfiltered, so it's a open optical band. So we get everything from about 400 nanometers to 950 nanometers. So we get some infrared leakage at the long wavelengths. But yeah, like Ryan said, the CMOS sensor has a Bayer filter laid over the pixels. So every group of 2 by 2 pixels, I don't know what I'm doing with my fingers. Every group of 2 by 2 pixels has 2 green pixels on a diagonal and then a red and a blue in the other corners. And so those do act like individual pixel filters, but yeah, that's all the filtering we have. You can attach filters to the eVscope, but we do not do it
by default.
By default.
Yeah.
All right, Bode's Galaxy is coming through a little bit, but yeah, I can definitely see the impact of the clouds. It should be a little bit brighter. Boom. Bode was an astronomer, I believe.
I'm going to fact check you on that.
Yes, what does that say? Enhanced vision something.
It says here that Bode produces one-of-a-kind handcrafted clothing cut from antique fabrics, Victorian quilts, grain sacks, and bedlines. So
That's
way
good.
off.
That's good for me. Thanks, Google. First hit.
Wait, I'm sorry. It says bode here means to be an omen. So it's actually an omen galaxy.
Doesn't bode well.
Johann Elert Bode.
German astronomer.
Yep. His claim to fame is winking in all of these photos.
Winking?
You know, like he's doing the
Interesting. Yeah. Let's see, 250 million stars in this galaxy, about 12 million light years from Earth. So this is one of the farther away galaxies we've looked at tonight. The largest galaxy in a group of 34 galaxies called the M81 group. M81 is Bode's galaxy, so it's got a whole galaxy group named after it. Spiral galaxy, but we don't really see the spiral arms well, if I remember. You see them a little bit, but I think because of its distance and the way it's inclined to our line of sight, you don't see them super well. Not like a Pinwheel Galaxy or a Whirlpool Galaxy, for example. It's in the constellation Ursa Major, which is where the Big Dipper is. Has a supermassive black hole at its center with a mass of 70 million solar masses. So if you took 70 million copies of our sun and crammed them into a point that's basically infinitesimally small, you'd have this supermassive black hole. That's pretty big.
I'm gonna send the telescope back, I think, because we have on the agenda that we were gonna close it up around 5:15.
5:15. Okay. Yeah. Do you want to? I was thinking
We could. Off.
Yeah, we could. If you still have energy for this.
Oh yeah. Absolutely.
Yeah. So the image quality is degrading quite a bit, chat, on the nickel. So we're going to close up for the night.
The return of roving Ryan is back, baby.
Yeah. So we'll keep the eVscope looking at Bode's galaxy, but we will switch to roving Ryan. However you do that. There we go. What is happening?
I was trying to figure out the best way that they could still see the eVscope, unless we just want to show it.
That's not an option, unfortunately.
Okay.
We'll come back to this. The eVscope will still be there.
All right.
Yeah. So yes, we will. Ryan will go into the dome.
Meant to do that. Then I'll turn on the mic.
And so I will, while you're in there, I'm going to close the mirror cover, Ryan. All
right, so this is the inside of the dome. For those who didn't see this at the beginning of the stream some very many hours ago, you can see right now, this is the nickel. It's actually very dark. It's kind of hard to see. Where the heck is the dome? The dome lights. There, the dome lights. This is what I lovingly call the danger ring, because they said that it is a danger to touch. So I do not touch it. But, okay, so we'll let Tom do his thing. But you can see that is the top of the nickel telescope. Here it is pointing out presumably to where our asteroid was. I hope that was the asteroid. Otherwise, that would be very sad. But yeah, we'll let Tom presumably begin. You can see this big dome here. One thing, dome's closing. So one thing you'll notice, for those who were not here at the very beginning of the stream, the nickel telescope is very close to the edge of the dome. There is really not a whole lot of leeway between the top of the telescope and the dome. And you may wonder why that is, and that is because this dome was not built for this telescope. This dome was built originally back in like 1888, 1889, with a different telescope at the time. And then about 50 years ago, sometime in the 1970s, Lick Observatory received a donation from Anna Nickel, who was a seamstress. She gave a donation basically to say, hey, you guys need a telescope. I will give you some money to make a new one. And they basically had this dome ready. And so they built it with as big as they could to fit it inside this dome that was not built for this telescope. But yeah, one of the funny things when we were talking with the support astronomer the other day about this is that the nickel telescope, they also call it sometimes the spare parts telescope. And that is because Anna, when she gave the endowment to make this telescope, she gave, it was like $50,000, which is a lot of money, but not to build a very, very large 1 meter class telescope. So you have to figure out how you are going to budget that. And so they made these support struts out of unused water pipes, and basically built the telescope like that as best they could. So it works great. It's fantastic, and it's got a little bit of character to it as well, and that it is the spare parts telescope, because it is a 1 meter class telescope on a mountain that has a 3 meter class telescope. They also use it to kind of test out equipment, test out different words are failing me this late in the evening, this early in the morning. Different techniques. So here at the edge of the dome, I will show you this little barcode. So one of the ways that you have to figure out in case the dome gets disconnected from the telescope and you need to send it home and it has no good way of doing that, it has to figure out where it is on its own. So this was one of the first implementations of a kind of magnetic barcode strip on the edge of the dome that it's magnetic. So it has a little computer that reads as the dome rotates, figures out where it is. And then when it gets to the part of the magnetic strip that signifies home, that's how it knows when to stop. So this was the first implementation of that. And it's something that other observatories are now also using. I don't know how many, but it does happen. So I don't know what Tom is doing. I expected him to start shutting down the telescope.
Can you hear me, Ron?
But we see here, it is a big lad. This right here is the Doer. This. You trying to shut down the telescope? No.
I was gonna, I'll put it in the dome flat position.
Oh, duh. Yeah, because we need you twilight.
We'll take one. So this
Yeah.
is up that I will start with your telescopes.
Yep. I am stepping back.
So put it in the dome flat position and
Yep.
go in and do it as well.
Yes. Okay. So this canister right here is the Doer that's filled with liquid nitrogen, and it is what keeps the CCD camera cool so that we can get the best images with very little noise. The detector itself is this golden box right here. And so that's hidden within there, and that's why it's connected to the Doer itself. Tons of wires that go to all sorts of things. I would hate to be the person that has to manage those cables. Let's see. I guess something else that's interesting. So the dome itself was not made for the telescope. You can see up at the very top there. Oh, actually, I'll shut up for a minute while the telescope moves. right. Yep, now the dome is moving. But it's an interesting design. If you haven't seen a large telescope before, the way the struts work is that it can rotate along this axis here, but then also the telescope is able to flip by rotating this giant structure, this giant kind of rectangle, rotates along this plate right here. So you have this kind of a yaw and roll, something. Yeah. So it's a not an intuitive way to move, but it is very cool to see. And Tom just opened the mirror back up. That's what that big click was. You can kind of see here. So let me see if I can get a good angle for you. No, I can't. Yeah. At the beginning of the night, we could show people the mirror, but it's not pointing the right direction anymore. But we can take a good quick look here. So this is a friction drive. Basically, there's a giant motor in here that when it rotates a little wheel here that is literally just friction moving the telescope around. So it pulls this big plate around, and that is what causes the telescope to rotate. Let's see, is that actually visible? Yeah, there we go. All right. So I'm not sure. I'm going to double check on what Tom is doing. I think that's, yeah, we're in the position. You can see the flat screen right there. So we can turn on some lamps to illuminate that screen, and that will let us take some flat fields. Yeah, where the heck is it? There it is. Let me turn off all the lights first, because that seems bad. All right, and welcome to the spooky Ryan tour. Aha. We're going to close this door because that's stray light. That's bad. We don't want that. Go. So yeah, for those who don't know, what we're doing now is taking a flat field. We took some earlier in the night, but it's always good to have calibration images at the beginning of the night and the end of the night. A flat field. Why would we do that? Why do we care? The idea is that your camera is not equally sensitive all across. Each pixel is a little bit different. No matter how good your manufacturing process is, there's always going to be some minute differences that can cause some pixels to be more sensitive than others. And so you want to be sure when you're taking data that the brightness of your target is not due to the pixels that it happens to be on being far more sensitive than the rest of the image. So we take these flat fields at the beginning and the end of the night, and they're called flat fields because it's literally just you illuminate a surface evenly and take a picture of that using your CCD. And because it is evenly illuminated, that should tell you theoretically that every pixel is getting the same amount of light, and then how responsive that pixel is tells you how sensitive it is, so that you can then correct for that at the when you're doing the analysis of your science images. That way you can be very, very sure that the brightness of your target is not in any way related to how sensitive your CCD pixels are across the CCD. So I assume that Tom right now is taking these images, which is why nothing's really happening. You just leave the lights on, and then you have the telescope take an image as normal, which this is what it looks like. But there are several ways that you can go around doing that. You can see here that this is still casting some shadows. So that is one of the downsides of trying to flat field this way. Oh, well, it helps if I'm pointed at the dang thing. There we go. So yeah, casting some shadows. So it helps to flat field if you don't have shadows, if your surface isn't curved at all.
So one of the other ways that we typically do this is we race the sky, we race the sun. There's a very, very limited portion of time at the end of the night, or at the end of the night and the beginning of the night, where the sun isn't up and it's not bright enough to disrupt your CCD, but not so faint that stars are out. So we call those twilight flats, and basically you have to point them in the sky, and you have to switch your filters really fast. And those are excellent flats to have, because then you have guaranteed no gradient in your image, no shadows, no curvature happening that could cause some portions to be more illuminated than others. But they're hard. They're very tough to do. And sometimes you just run out of time. Like, that's just the thing. So these work in a pinch, and they're still pretty good in general. It's just, they're not perfect. Everything that you do has a trade-off. You just have to decide what it is that you need most when you are doing science. Okay.
So I'm going to finish taking flats. So,
Yep.
If you want to come out.
Oh, the light.
All right, goodbye.
All right, so we are back, and we'll finish. Why did my sound effects go away? Did I turn? Nope, there they are.
Bing.
Where am I? What am I doing?
Yeah, if you were listening to me in there too, it was just like, all right, I get halfway through a sentence and I lost it.
Yeah. All right, here we go. So that's what we're doing. Righto. Go over here. All right. Yeah, chat. So we are looking at, on the right-hand side, this is the image that we get from the camera when it sees a somewhat uniformly illuminated field of view. You can see by this color stretch here, I can make it gray again if we want. But it's brighter in the middle and darker at the edges, so it's not actually uniformly illuminated. But it does allow us to see things like these donuts in the image, which are caused by some sort of dirt or dust that's on one of the optics somewhere in the telescope, one of the mirrors, maybe the entrance. There's a window that covers probably the camera. I'm not entirely sure, but it's pretty common. A transparent window. Any sort of dust particles on those surfaces will be out of focus because the telescope is focused on infinity, far away in the sky. And out of focus things will look like donuts in your image. Delicious. So these donuts are in all of our science images. You probably saw them while we were taking images before. But when we divide those science images by these flat field images, it will essentially compensate for the donuts. Everywhere in this flat field image that the values are low, dividing by that low value will make the value of those pixels higher. And therefore, it flattens the response of the sensor to light that hits it, and that's the whole idea of the flat field. So we're going to take about 5 of these in every filter. We're doing the B band right now. That's the blue color of light. They're 30 seconds each. You can see that in the exposure box here. And we are recording, making sure we write those images to file. We didn't really explain this recently. It's been 13 hours since we talked about this. But this window here is the camera control. And so you see these messages at the top. The first one will be yellow, and it will say erase begun or something like that. And that's it's applying a uniform voltage across the entire sensor in that camera. And that voltage effectively wipes the slate clean. It's like shaking the Etch-a-Sketch, if anyone here is old enough to sketch, so that all the pixels have about the same baseline value. And that value is called a bias, voltage bias. Once that's done, then it, I think at that point it opens the shutter. I'm not sure if it opens the shutter. Let's see. So we're gonna let me put this.
I think it doesn't open the shutter first because it wants to make sure that it's clearing everything.
Right. I would assume, I'm going to move this over so you can see what I'm doing. I'm assuming it then opens the shutter. It starts exposing, exposes for 30 seconds. And then when it's done exposing, we'll see what happens in a second. I'm going to change the filter to V band, make it move. It's moving the filter wheel that has filters in it into the right position. We're going to decrease the exposure time because the lamps that are illuminating that screen are brighter in the visible green band. I'm going to take an image. The start exposure button starts the exposure, so it's erasing those voltages and setting a constant voltage value. It's exposing, so we requested 4 seconds. 4 seconds have elapsed, and then you'll see it reads out for about another 20 seconds. And now it is taking the voltages that were measured in the sensor, and the voltage that in the pixels is created by the photons, the light rays that are hitting each pixel. Each one creates a little bit of charge, which we measure as a voltage. That voltage gets shuffled along the columns of that detector. 36,000 is a little bright, but good enough. Then passed into electronics that turn that voltage, which is an analog value, into a kind of quantized set of numbers, which is a digital value. Those are the counts that we see in this image. If you look in the right corner here, the value, those are units of detector counts. And so those are what we use as intensity values for each pixel, basically how bright that pixel is. And from there, with various calibration tricks, we can turn those brightnesses, if they're stars, for example, into magnitudes or Janskys, units of flux, or I don't know, whatever other godforsaken units astronomers use.
Paul Shields asks if that vertical line is a sensor defect.
It is. So it's this column of pixels. I can probably zoom in on it. You can see it's just one column of pixels. Something about the electronics for this column, the voltage is not being set properly, and so all these pixels are saturated. They're full of electron volts. So this column is garbage. It's hopeless. We just will filter it out of our images when we reduce. That happens. Just about every every camera has something like that. It's very hard to make a silicone chip like this that's got 2,000 by 2,000 pixels. That's absolutely perfect. There will be bad pixels scattered around these images, usually pixels that just don't respond to light in the way that the others do. And again, those get calibrated out by things like the flats and bias frames.
Antenna temperature is the most cursed of the intensities. I still don't know how that works, and I'm upset that they call it temperature, quite frankly.
because it has nothing to do with temperature.
It does have something to do with antennas.
I didn't learn it.
Yeah, I don't know.
I
It's
refused.
radio stuff.
I refuse to learn it, and Leisha Van Zee, if you are watching, I will never learn it. I'm sorry.
Well, come after him. All right, we're gonna move.
She probably would.
We're gonna move to R band, and in R band we're gonna use a different set of lamps. So we'll turn off these lamps that are mounted on the telescope, and we will turn on the lamps that are mounted on the dome. These are just better for these longer wavelengths. Looks like everything is good there. We are in the right filter position. We will increase to 5 seconds. Recording, and I think we're just gonna go ahead and take 5 images.
I'm gonna have to look up antenna temperature now. Oh, I'm gonna have to learn it.
It's way too early to start learning radio astronomy. Well, Bode's Galaxy has turned out nicely.
Ooh, yeah, that's fantastic.
You can see those spiral arms. Here's a really good one. Down here, chat. You can see those empty spaces between the arms. Also here. Let's see, we just entered past 12-degree twilight, so getting to the point where that eVscope image is not going to get much better. Hopefully it won't get worse. What is going on here? Oh, right. This is the VNC, so that's why I can do that.
This is why no one should use antenna temperature, because I can't even check if it's in measures of Kelvin without having to look up what the units of the Planck constant are, because I do not remember off the top of my head.
You're saying words, but I'm just hearing blah, 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 blah.
You're hearing me whine.
Yeah.
Joules per hertz. Yeah, I don't think it's Kelvin.
And yeah, we've got one more after this. Then we will just take 10 bias frames. So I'll describe the bias frames now to save some time.
Oh, decibels for Kelvin, maybe.
We will close the shutter on the camera. So we will let no light into the camera. We will set the exposure time to 0 seconds. So that means that basically the camera will not record anything except the electronic noise that happens when you read out the image. There's always some noise when you're dealing with charge, like we're dealing with electric charge. There are quantum fluctuations, for example. There's also just, you get a little bit of noise when you're moving a charge from one pixel to another, and a bunch of other things. So
I take it back, Paul. You beat me. You're right.
decibels per Kelvin. Is that what it is?
Dude, radio astronomy is the worst. I don't understand it.
Decibel log. Oh, it's a log unit too, logarithmic unit, so that makes it even more terrible. Yeah. Yeah, and then we will, that's it for the biases. The CCD does not have significant dark current, so we don't take dark frames if you're familiar with other cameras. Dark frames would be taken with the shutter closed, but the same exposure time as your sun. And this would capture the thermal noise in the sensor. Because the sensor is not at like absolute zero temperature, the energy imparted to the electrons in the chip from the temperature of the chip will sometimes be enough to pop out of the little silicone wafer into the
actual detector.
What is the band? I forget. Across the band gap that they need to jump across to be counted basically as a signal. And that can happen just kind of sporadically. And so that's one of the ways you get dark noise. In this case, that dark noise is pretty low, so we ignore it. I've skipped a lot of details here. Hard to explain.
No, I mean, I think it's still a reasonable explanation.
Yeah, a picture really helps think about the voltages and stuff, but another time. Let's see, this is our band. I hope Ryan is checking my work because these are getting blurry.
You're driving, so I don't understand.
Oh my God. Maybe we should walk down the mountain.
No, it's fine. I've got a whole half a pot of coffee left. I'm just going to take it with me and not tell the support astronomers that I've taken their coffee machine with me.
No, that would be mean.
It would be mean. And as we have determined, we like the Lick Observatory, where we are currently at. Think they're great. Hashtag not sponsored. We just really like the observatory. And you should donate to them or come up with a tour and see some really cool telescopes. 10 out of 10. Would recommend. Hashtag not sponsored.
Indeed. So let's see. So we're not using the guide camera anymore. We never actually used it tonight because we didn't look at anything that stayed still. So I'm going to shut down the guide camera software so that it's not being used when we don't need it. This is one of those GUIs that you got to find the right way to shut it down. And quit. You do not choose quit. You choose shutdown guide. Fun little game we play. So we'll shut that down. And actually, we will need to shut down all the GUIs because this is our last night for this run.
Yep.
Hard-boiled egg.
Hard-boiled egg. We didn't buy any eggs. We could have.
Yeah. I don't know how I feel about eggs when I'm trying to go to bed. They are a good breakfast. Okay, that was the end of the flats. So I will now turn off the flat lamps entirely. Off. We've got little dome cameras that will see if the lights go off. They do indeed. I can close the mirror cover because we're not going to get light to the camera anymore. I will close the shutter on the camera because we're going to do biases. Set the exposure time to 0 seconds. I will change the object name. I remembered.
Proud.
To bias.
That is admittedly the hardest part.
Yeah. And we're just going to take 10 of these.
Nice.
Nice. So this should go out pretty quick. It's about 20 seconds per image, so maybe 22 seconds per image. 220 seconds. It's like 4 minutes. We'll be done. I can turn off telescope. I should park the telescope.
Yes. Please.
So we will do functions. Park telescope.
Do you really want to park the telescope? Yes,
No.
please. You worried about the bias?
No, I was thinking I'm going to share this instead. Should I? Just
put an egg in with the ground. That is a choice.
Park telescope. So the telescope will now move to zenith. It'll point straight up, where it's nice and balanced and happy.
You're welcome, Lars. We've been streaming for a while, but we're glad you could make it either way. Hopefully there will be more things like this in the future, depending on when we get time, or maybe we'll inspire some other astronomers to also try something like this. This has been a fun experiment for us, I think. For those of you who don't know, neither of us, Tom or I, have ever live streamed anything before. So
it was a choice to decide to go for 13 hours for the first live stream, but I think it worked out pretty well.
Everything's easy from here on out.
Yeah, you all have been a fantastic audience.
Yes, thank you. Thank you very much. If you want to go back, the recording should be on YouTube. It may be broken into 2 chunks.
Yeah, because there's a 12-hour chunk and then a 1-hour chunk.
Yeah, I have no idea how that will appear on YouTube. Hopefully it worked. At the very least, I think we have our own internal recording somewhere in the cloud, and so we can repost that perhaps if needed.
Mm-hmm. If anybody goes through the entire 13-hour recording of this, let me know. Genuinely, I'd be very interested to know if somebody went and sat down for 13 hours to rewatch this.
Yep, thanks, Daffodil.
Yeah, appreciate it.
If someone does do that and watch the entire thing, if you feel like coming up with timestamps for particularly interesting or fun things that happened, send that our way. I have a vague idea of
where things were.
No, I have no idea when things happened. It's way too much time, but I have a vague hope that someday I'll be able to edit this down into about 2 minutes of video.
Okay.
I don't know. You know, most of it was us babbling.
Yeah.
We're trying to figure out what the asteroid is. And I think maybe that would be a fun thing to share on something, a shorter format like TikTok or Instagram or something. The odds of me ever getting the time to do that are really, really, really low. But maybe we can convince one of our communications friends to do it. We can download the Twitch VOD and post it on YouTube with free tools. Handy. Good to know.
I have noticed getting random YouTube recommendations for, I guess, streams or videos that have like 1 or 2 views. So that's us now. We got there. We got recommendations.
Woo!
Steve got recommended. Well, I'm glad you stuck around. Thank you for giving it a shot. I do think while we're waiting,
Yes.
it's a real shame that we never got to play the game that I devised for Tom.
Hit me.
Okay. This is a game I'm going to call Yes or No.
Mm-hmm.
The fun game where I ask Tom questions and he can only say yes or no with no elaboration.
Okay.
Okay.
I'm ready.
That's the rules.
Yeah.
You can only say yes or no.
Yes or no?
I
say
no. I will.
C or
I
no?
am pulling up an extremely loud incorrect buzzer as we speak. Extremely loud.
I haven't heard enough dings and chimes today. All right, here we go. We got 12 minutes until live stream ends. So.
Okay. So, first question. We'll start you off easy. We'll make something simple. All right. Is your name Tom Esposito?
Yes.
Really? Okay. That's good. That's good. I'm waiting on this. So let's double check this.
What do you do?
I was going to try and do the loud incorrect buzzer, and I realized that didn't work.
Let's skip that.
Fine. All right.
Yeah.
So your name is Tom. You can only say yes or no. All right. Second, easy question. Real simple. Are you a SETI astronomer?
Yes.
Okay.
Yes.
Okay. Good. Do you like California?
Yes.
Oh, yeah. So would you prefer, I know that you have lived in other places besides California. Would you prefer living in California or in your home state of New Jersey?
No. No.
Okay, so home state of New Jersey is not preferred.
No.
Understood. I feel really stupid now. This is great. What's your favorite thing about being from New Jersey, Tom?
No.
Okay, good. I'm glad you're keeping to the rules.
Yes.
Do you like jazz?
Yes.
Weird. Wouldn't have thought that about you. Pineapple on pizza?
No.
No. All right.
we're done here. Ants. Ants?
No.
No to ants. This one's okay. So this one's actually a serious question. Why don't you bring your dog to the office more? And is it because you worry that I will become Albie's favorite?
Yes.
Yes. Can you elaborate on why you think exoplanets are a boring topic of research?
No.
Tom, I think I know the answer to this already, but can you explain why you hate baseball so much?
Yes.
You can. That's good. I'm glad. I'm also going to take this banner down. You've mentioned on multiple occasions that I'm actually your favorite person to work with. Why is that?
No.
Okay. And are you ready for this bit to be done?
Yes.
This was an incredibly stupid game. I'm sorry. Thank you, everybody, for putting up with it. I came up with it in 5 minutes and immediately decided that this was something I wanted to try and do. But when we got into this, I was too awake to think it was a good idea. And now that we're nearing the end of the stream,
this is the perfect time for it.
This is the perfect time for it.
All right. We're in the process of shutting down here. We are done with the telescope for the night. Ryan, what else do I have to do here? So let's see. I need to pull up the guide. Where is the
notes?
Where's the guide? Shut down. I know we need to close the GUIs, but it would be nice if there was a script that did it all for us.
No, I think we have to do it one by one.
Do it one by one.
Mm-hmm.
Okay.
Checklists?
Yeah, that's what it was. There was a checklist. In the control room, take dome flights and darks, park telescope, disable movement, close mirror cover, turn off fans.
Fans are already off. Dome's closed. Windscreen doesn't exist.
Good. So that's done. Check telescope or dome and stow positions. So we'll do that before we walk out.
Mm-hmm. Emergency stop. We'll do that before we walk out.
Yeah. Do we actually do that? I guess.
I don't think so, but
it wasn't mentioned. There is no rain screen, ventilation, fan shutters. Okay, I don't know if we do all these things.
Yeah, I don't think
we don't
do.
fill the Doer. Leave dew sensor on. Oh. I'll download the data another day. Leave dew sensor on, fill out user in trouble odds. We do need to call the telescope operator in the Shane, so I'm going to call them now.
Yep.
And tell them we are done for the night. That's about it.
Turn off lights. So I'll close GUIs while you call.
Yes, I just need to find the number again. It's 80652. All right, it's all yours.
Oh yeah, no problem, Will. Thank you for stopping in, especially because you were here for the entire 13 hours, which is insane to me. Yes, the GUIs are Linux. All of the computer that we're running on is a Linux machine with some virtual Windows. All right, and now we get to the hard part of playing the game. Is this a thing that I can just close, or do I have to find the hidden quit button? Exit, yes, exit. File, exit. Quit.
Hi, this is Tom Esposito in the nickel control room. We are closed up for the night. The dome is shut, telescope's parked, mirror cover's closed, and we're shutting the GUIs down. If you need anything, we'll be in the control room for the next, 15, 20 minutes at least. So thanks for your help. Have a good night.
All right. Quit, yes, really exit. Nickel event sounds, quit. This we can just close.
I'm gonna start packing up.
Yep. All right. I think that's it. I think we are officially closed up. So where's our camera? There's our camera. There's our camera still, which I just can't see it anymore on here. Boom. There we go.
Indeed. Yep. Stop sharing. We're done. Chat. eVscopes going to bed.
Mm-hmm.
It's still running. It's chugging along.
Ooh, it's trying.
Collecting a lot of daylight at this point. I can see the edge of the building now, which means the sun is rising.
Yep.
Yeah, I don't think I said it, but thank you everyone for your support, your attention, your questions.
Yes, it should be on YouTube the first
12 hours. We think that it's split up because we had to shut off the stream and start it back again. But if it's not, then it's available on Twitch. It should be available on Facebook Live, although that's also probably split up into 2 chunks. And if it's not available in one chunk on YouTube, then we will download the VOD on Twitch and upload it to YouTube as one complete package. So we will make this available as easily as we can in one complete package. So, on that note, I think we will bid you all adieu. Thank you again so much for supporting this experiment, being such a great audience, asking us lots of fun questions, and just generally making this night incredibly entertaining for us. We couldn't have done this without you. So good night and good morning, depending on where you are in the world. And we wish you all well, and we will see you next time.
Bye, everyone.
Bye.